Today we want to talk about assignment 1 on forces and equilibrium. Now, on assignment number 1, we were given these easy, medium, hard, and very hard questions, and they were based on Newton's second law of motion. Now, in our notes, which I've given all of you, we've stated that Newton's second law of motion says the net force acting on an object is direct proportional to the mass times the acceleration of that object. The net force. So this is how we defined it. So the net force, so let's say the net force here, because we need to understand what net force is. So net force is actually not the force applied on an object, it's the resultant force. So the Newton's second law of motion says the net force acting on an object is equivalent to the mass times the acceleration of that object. So now let me just explain in a short what net force means. Let's say we've got an object, okay? We've got an object here which is moving on a plane which has some friction to it. Let's say this friction going here, opposing, okay, is 20 newtons, okay? And then the force that is moving this object in that direction is 50 newtons here, okay? Now, if you look at this, is the force that we are applying here. This is applied force, okay? Applied force, okay? And then there's friction force here, frictional force, okay? Frictional force here, which is opposing the motion. That's what we've been stating in physics all along. Now, if you look at this diagram here, the force that is acting on this object and making it move is not 50. It has to be the difference between 50 and 20, since 20 is opposing 50. So the net force by Newton's second law of motion is actually 50 minus 20, which means you've got 30 newtons acting on this object and making it move this way, okay? So when we say Newton's second law and we state that the net force acting on an object is equivalent to the mass times acceleration of the object, we mean this 30 now in this scenario. So now let's say the acceleration of this object going in this direction here is 2 meters per second squared, and the object is actually 15 kg, okay? So it means by Newton's second law of motion, we say the net force, which means 50 minus 20, so the resulting force is 30. This 30 must be equivalent to the mass, which is 15, times the acceleration of the object to give us 30. So these must always be balancing, and we must not make a mistake where we take that the force applied is equal to the net force. The force applied is equal to the net force if there is no friction involved. I'm just trying to run a review on this Newton's second law of motion. So the net force is equivalent to the applied force if the object that is moving is not experiencing any friction or opposition. So I hope this is a very brief explanation of Newton's second law of motion. Now, based on this law, this is where we made this assignment. And today I want to focus only on medium questions. So question number 1, you can see they're saying in each of the scenarios depicted below, the forces acting on the body cause it to accelerate as shown, okay? So we've got this diagram 1 here. So there's this body of 4 kg, and they are saying it is accelerating as shown. See, this arrow is telling us that this body is moving at 2 meters per second squared. All right. The acceleration due to gravity is defined by g. So this g here, they mean this is acceleration due to gravity, okay? Now find the value of the unknown variable or variables a, m, or p in each case. So we've got these 3 cases here, and we want to use Newton's second law of motion to find the value of g in this case. Now what we know is that we are talking about forces. What we have is 4 kg here, okay? This is 4 kg, the mass, okay? And then this 2 meters per second squared is the acceleration of the object. Now, if this is the mass, we must know that weight, which we sometimes can say the force, okay, is equal to mass times acceleration due to gravity. Now, the mass of this object is 4 kg, okay? And we know that acceleration due to gravity, in this case, we are going to take it as 10 meters per second squared. Okay, so to know the force that is opposing, to know the force that is making this thing move, okay, we are going to say the force of the object is 4 times 10, which is acceleration due to gravity, to give us 40 newtons. Now, this 40 newtons here is the force that is wanting this thing to move down. But there is another opposing force going in the opposite direction called P. Okay. Now, what we know from Newton's second law of motion is that the net force between the 40 newtons, okay, and the P must be equal to the mass times acceleration of the object. So to find the value of P, we know that 4G minus P, okay, this gives us the resultant force that is making this thing move at 2 meters per second squared, should be equal to the mass. The mass is 4 kg, 4 times the acceleration 2. Now, in this case, this is the net force that we just talked about here. Now, you remember that acceleration due to gravity is mainly given as 10. So we know that this is going to be 4 times 10 minus P equals to 8. Okay. Now, if we do that, it's like we've got 40 minus P equals to 8. And if we do our algebra by transposing 8 and P onto the other side, we're going to have a situation where we're saying P is equal to 40 minus 8, which means P, which is the force that is opposing this movement, is actually equal to 32 newtons. So in diagram number 1, this P here is equal to 32 newtons. So this is equal to 32 newtons. And then the force going down was actually 40, meaning the net force that was actually making this thing move is simply 8 newtons. Now, this is our understanding and direct application of Newton's second law of motion. Now, for B, what we are going to do now is the same thing. All we are doing now in this case is, it's the same thing. So we've got an object with m mass that is moving. You know, the arrow for the acceleration points you in the direction of movement. So we are going to take the downward movement as positive movement. So we know that this object to move at 6 meters per second squared is being facilitated by the net force of mg minus 70. So we know that mg minus 70 should be equal to the mass times the acceleration. Now, this mass we don't know, but the acceleration we've been given as 6. So now, what we know is that g is acceleration due to gravity. So it's like we've got m times 10 minus 70 equals 6m. Okay, now here we've got 10m minus 70 equals 6m. What we are trying to find is the component m. We can transpose 6m here and then transpose the other guy there. So what we are going to have now in this case, let me bring this here to have enough space. What we are going to have now in this case is 10m minus 6m equals to 70. And we know that 10m minus 6m gives us 4m equals 70. We want to find the value of m, which is our mass. We divide by 4, and then right there we know that m is equal to, when we divide 70 by 4, so 4 divided by 70 divided by 4 gives me 17.5 kg. So this is 17.5 kg. So you can see we are just doing a direct application of the Newton's second law of motion. So now what we want to do now here, I think the unknown is acceleration, but we've been told the direction because the arrow where the acceleration arrow points, that's the direction of movement. So we're knowing that this 10g minus 88 should be equal to the mass times acceleration. So we know that 10g minus 88. We are trying to find the net force that is causing the movement of this 10 kg thing times its acceleration here. So now we know that g is 10 meters per second squared. So this means we've got 10 times 10 minus 88 equals to 10a. So now this gives us 100 minus 88 equals 10a. And then if we do our math nicely here, this gives us 12 equals 10a. We want to find a, we divide by 10. We divide by 10 to mean that acceleration for this, which is the missing component here, is equal to 1.2 meters per second squared. So that's the acceleration for that. So this was for question number 1 on medium questions. What is important is understanding that the net force means when you take away the opposing force from the force applied, what you have is what we call the net force. And that net force should be equal to the mass of the object times its acceleration. And that's what we are just using here to find the missing components. So let us now look at question number 2 and see if we can do anything on question number 2. We'll look at that one. All right. So this is question number 2 here. Question number 2 says, as part of a stage show, a singer is lifted up in the air by a cable attached to a special harness. The singer has a mass of 54 kg and at the start of the lift is standing stationary on the floor. Okay. The singer accelerates vertically upwards at a constant rate and after 2 seconds has reached a height of 3 meters. By using the appropriate formula, determine the acceleration experienced by the singer using the lift. Now here, diagrams are important. Okay, so we've been told, so I'm going to use both sides here. We've been told that there is a singer here who is on stage. So let's just try to have this singer here and see if we can model this situation. So there is a singer here who is on the floor and he's got a mass of 54 kg. Okay, and then when is lifted by this harness, cable, tension, or whatever it is, let's call it T here, after 2 seconds, which is T, so we've got T, which is 2 seconds. Okay, then we've got a certain height you'll get to after 2 seconds. Now height, if you want, you can say that's the displacement. We've got 3 meters, okay, after 2 seconds. And this guy has that. By using the appropriate formula, determine the acceleration. So you know how we do it, SUVAT. You just write SUVAT. So you write your SUVAT here, there. What we have is displacement. We have time. They are asking us to find the acceleration. They have not talked about velocity, but we do have the initial velocity, because when this guy was yet to be lifted by the harness cable, he had that. So in other words, we are looking for the equation that has displacement, that has initial velocity, that has time, and then it is only missing the acceleration. If you've worked nicely with your SUVAT equations, you would find that it is the displacement equation, which goes displacement is equal to initial times t plus half 80 squared. So if you look at this equation here, it's got everything that we need with the exception of acceleration. Okay, so what we are going to do to find the tension in the cable. Okay, so first, A says find the acceleration experienced by the singer during the lift. What we are going to do now is we're just going to replace our values for t, because our u, initial velocity, we know is 0 meters per second. So we just need to substitute these in there. And our x is 3 meters. So what we're going to have is 3 equals 0 times t, which is 2 seconds, plus half times a times the time, which is 2 seconds squared. And all we need to solve. This is going to be 0. Then we've got 3 equals this is going to give us 4. 4 times a gives us 4a over 2, and then here we can just cross multiply to give us 4a being equal to 6. And if we divide by 4, we divide by 4, we find that a is equal to what you get, 6 divided by 4, to give you 1.5. So it means the acceleration is 1.5 meters per second squared. This is our acceleration for B. So what is important is actually looking at the variables that you have, and then once you have that, you can then work it out. So this is our answer for A. Now for B, they are saying find the tension in the cable during the lift. So now we're going to have to model this situation. Let's say this is the situation we have here, and we have our single. Okay, so this guy now, he is the one here. Okay, so let's say we've got this guy here, down here. This is the singer who's got 54 kg, and then there's tension T in the cable. This is the cable here, this red line here. This is the tension they want us to find. Okay, remember this guy was going up. The question says it's being lifted up. Now the weight of this thing here is actually 54 g. So this was meant to be 54. Okay, so this should be 54 kg. Okay. Okay, so to answer B, we are going to model this situation. This is the string, and that's the tension they want, because you see the force that exists in the string is called tension. And this guy is going up with acceleration that is given as 1.5 seconds squared, because we just found that. Okay, and then he's got 54 kg, meaning his weight going down, the opposing force that is opposing the movement of this person going up is 54 g. Okay, because we have to multiply the weight, the mass, by the acceleration due to gravity to know the weight force. So this is the situation that we have now. So we know that for this person to move up going there, the movement that is causing this person move at that speed, okay, or at that acceleration, is actually equivalent to the net force. But we know that the force that is making a move is T. So we've got a T minus the force that is opposing the lift is 54 g, which should be equivalent to the mass of the object, which is 54, times the acceleration of 1.5, because we already have acceleration, and we know now that G is 10. So what we're going to do is tension is equal to 54 times 10 equals 54 times 1.5. So if I punch that on my calculator, I get 81. So this gives me 81 here, and then here this other side I've got minus 540 equals to 81. So what we are now doing here, we're trying to calculate the tension. We transpose this to mean tension is equal to 81 plus 540, and this gives us the answer of 621 newtons. So in the tension in the string is actually 621 newtons. So the diagram does really help in these questions here. So that's our tension there. So what we just needed was to know that the tension minus the weight force, which is 54 g, should be equal to the mass times acceleration, where the mass is 54 and the acceleration is what we found here at A as 1.5 meters per second squared, which is 1.5, and then working out this to give us T being equal to 621 newtons, so which is the answer for B. And then C says after the show grand finale, the singer is lowered, okay, is lowered downwards back to the floor. During the initial part of the descent, the downwards acceleration is constant, which means we're still just using the same is constant and its magnitude is the same as the magnitude of the upward acceleration. So that means is the same as the upward acceleration. That means we are using the same acceleration in this case. It's dropping at the same speed while the singer was being lowered. Okay, so we know that when coming down is just the change in which force has gotten bigger. So then they say find the tension in the cable during the initial part of the descent. So we know that in this scenario now, this person is actually now coming down. Okay, so that changes the game now. This means the tension in the string is now not the bigger force to some extent. The weight of this person here, who is 54 kg times the g, okay, which is 54g, is now bigger than the tension in the string. But this person is coming down with the same acceleration of 1.5 meters per second squared, because that's what the question says. So here they are just now testing our understanding. They now want us to find t. So what we know is that 54g minus t should be equal to the weight, which is 54, the mass times the acceleration of 1.5. So basically this is almost like the same thing, but you see where the difference is. G is 10, so we've got 54 times 10 minus t equals 81 here. In this case we've got 540 minus t equals 81. We'll transpose the t and transpose the 81 to mean t is equal to 540 minus 81. And then in this case now, when we do 540 minus 81, we get the tension in the string to be 459 newtons. So this is our solution here, 459 there. So this question, they are just saying when it gets to that height of 3 meters, it changes and it starts coming down with the same acceleration. Can you now find the tension in the string? This should make sense, because for this string or the harness cable to pull the person up, it means the force in the string was actually bigger. But if it is to start coming down, we must reduce the force in the string and make the weight of the individual greater than the tension in the string. So they're just now swapping the question. So this is question 2 of assignment, and on the medium part of the question. So still on Newton's second law of motion. Let's look at number 3 and 4, which would be the last questions. I think the other questions should follow the same order. So let's look at that. Okay, now for question number 3, a child is pulling a cart along a horizontal path. So here I think it should be simple. We need to model this scenario. So that's a horizontal path, and then we are told that there is a cart that they are pulling. Okay, so let's try to just draw this. Okay, so this person, maybe let's say this is the cart here. Okay, so the cart has a total mass of 15, so let's say this is 15 kg. Okay, already here we can maybe say, okay, the weight of it is 15g, in as much as it may not be important, looking at the fact that it's moving in its horizontal direction. Now, and as it moves, it experiences a constant resistance. These are very, very important. Constant resistance of magnitude 2n. So resistance means this is the opposing force. So let's say the opposing force of 2 newtons is in this direction. And then remember, we've been told that this child has attached the horizontal rope. So this rope here, you know, the tension that exists in ropes is called, the force in ropes is called tension. Okay, as T. So right away we can actually start thinking through here. The cart starts at rest and accelerates at a constant rate after 5 seconds. So here we are given something to do with time, which is 5 seconds. Okay, so we've got time given as 5 seconds. So let me just do that proper. So our time is given as 5 seconds. And then they say acceleration is given as 2 meters per second at a speed, so not acceleration. So we are also told that the speed, which is velocity now, our v is 2 meters per second. Okay, find the acceleration of the cat. Now we've got time, okay, time given. We do have the velocity given, and then they're asking us to find the acceleration. So if we go onto our SUVAT, we need to check what do we have. So what we have is the velocity, which also means we've got the initial velocity, and then we've got the time. What they want us to find is the acceleration. So what we need to actually do here, this is basic maths. We actually need to find an equation that has velocity, that has time, and initial velocity, because that's what we have. So right away, I think we should know there is a formula which states that acceleration is equal to v minus u over t. So these are the three things that we actually have, because remember the cat starts from rest. So what we're going to do to find the acceleration of the cat here, we know that it's in final velocity, which is 2, okay, minus 0 over the time of 5 seconds. So if we do this on our calculator, you'd find that this is 0.4 meters per second squared. So this is 0.4 meters per second squared is the acceleration of this body. So we know that this body will be moving in that direction there with acceleration of 0.4 meters per second squared. Now we have the acceleration, we've got the mass, we've got the 2 newtons that is opposing the motion. Then we can even be asked what the force that was applied in the string to make it move at that. Look at the question B, the tension in the rope. So now they want us to find what was the applied force that was experiencing a resistance of 2 newtons, and then its net, whatever the net was, made it move with the speed of 0.4 meters per second. So we know that Newton's second law of motion states that this applied force we are trying to find, T, minus the opposing force 2, should be equal to the mass of the body, which is 15, times the acceleration, which is 0.4. So here we've got a situation of T minus 2 equals, then 15 times 0.4 times 0.4 gives us 6. And then we know that the tension is actually going to be 6 plus 2 to give us tension equals to 8 newtons. So the tension or the force that was applied in the string is actually 8 newtons. A very good question. I like it when it starts with the SUVAT and then we revise some SUVAT equations. Let's look